Okay, what we're going to talk about in this lecture and then maybe the following one is the non-ideal factors that you have to deal with if you're using real op-amps, right? So we made some assumptions regarding the operation of these op-amps, and we'll see some of those, are not real. Basically, anytime we talk about something ideal, we talk about something that we really like, but what we get in real life is different, hopefully not that different. And some of those differences we'll talk about today, and then we have a speed limitation, which is a major factor in designing circuits with op-amps. I'll talk about it over the next lecture video. So going back to the previous discussion, what we saw was that you have a block here. We know that inside it there is a whole bunch of transistors that are dutifully doing their tasks, and we have biased them properly. Somebody has taken care of all the biasing and, let's say, gain adjustments, and you will see frequency compensation and those types of issues before. You have two signals applied to this device, and it gives you an output that is only proportional to the difference between the two inputs. So the common mode gain is 0. The differential gain, AV0, that I show here, is for an ideal op-amp infinite. So the assumption is that AV0 approaches to infinity. And we said that another assumption we make is that I plus and I minus, let's just put them I plus and I minus. These are the input currents inside the op-amp are 0. And with these two golden rules, we went and solved a whole bunch of problems. We saw a lot of interesting circuits now. We see that we can add signals, we can differentiate them, we can integrate them, we can, do all sorts of interesting functions with the signals that we have. And now that we know we have this super powerful device at our disposal, we want to see what are the limitations. And then if you're going to do the same type of work with real devices that you can buy off the shelf from a supplier, what are the factors that you should be careful about? During the live sessions, what I'm going to do is that I'm going to go through the data sheet for maybe 1 or 2 op-amps and tell you how to read different specifications for these op-amps. So I highly encourage you to attend those. But right now, we want to again go back to our circuit models and slowly try to see what happens if we relax some of those ideal assumptions. So the first thing that I'm going to see is, or talk about, is that AV0. We assumed it is ideally infinite. Practically, we know that never happens. Practically, we know that, an infinite gain means that you get an infinite amount of power from 0 input power. That's not physical. That's not going to happen, right? What is going to happen is that if you buy an op-amp and look at the gain specification for that op-amp, or look at the charts and try to estimate the gain, you'll see that it has a gain of typical op-amp somewhere between 100,000 and maybe 10 million, somewhere in that range, probably closer to maybe a few 100,000 to a few million in most cases. And that's a DC gain. We'll talk about the speed limitations in a second. So it's still a very large gain. You're talking about the gain of a million, 10 to the 6, but it's not infinite. And then for those of you who are interested in integrated circuit design and maybe looking at these devices in ICs and analog ICs, you see that the op-amps that we use over there are usually much simpler, so you do not have this full, let's say, biasing network, all sorts of compensation, everything else going on with a discrete op-amp that you buy and use in your circuit. The op-amps that you use in integrated circuits are usually much simpler, made of maybe, in some cases only 3 transistors, but maybe 5 or 10 transistors. And these op-amps, because they are so simple, will have limited gain. So usually a gain of 1,000 is quite a lot. Maybe a gain of 100 or a few hundred is more common or more expected. So nonetheless, even with a discrete op-amp, you have a limited gain. It's not infinite. So let's see what happens if we make one of those circuits with an op-amp with a finite gain. Let me go back to inverting amplifier, but this time assume that the gain is not infinite. Okay? So let me draw the circuit again here for our reference. So from the op-amp basic properties, I know that V out okay, so this is the definition of the op-amp. We are going to assume this is still holding, but because AV naught is not infinite, I cannot say that the difference between the two is 0. Now in this case, V plus is 0, or the voltage at the non-inverting input. So I can see that the voltage at the inverting input is the voltage that you have at the output divided by the gain. Right, so it's not 0. If AV naught was infinite, that would have been 0. It's not the case in here. So I have a finite voltage. It could be tiny. It could be, even, microvolts or so. But I have some non-zero voltage at this inverting terminal. Now, keeping the other assumption in place, that the fact that I in is 0 here, keeping that one, and that one holds in most situations. It holds better than this assumption of infinite gain. What I can do is that I can say, okay, for the voltage, for resistor R1, if I look at the voltage drop across it, VR1 is V in minus V minus, and that is equal to I, let's call it I1, R1. And from here I can calculate I1. So I1 in this case is going to be V in, and then I have a value for V minus for the inverting voltage. So the ideal device that was faithfully converting the voltage into a current now has a little bit of non-ideality in it, right? So the current is still mostly proportional to V in, but there is a contribution from V out in here as well. Now, because I in is 0, all of this current has to flow through R2. Same discussion that we had before. If I look at the voltage drop across R2, what I can say is that VR2, which is V minus minus V out, is I1 R2, because all of I1 goes through R2. And then if I plug the equation from the above in here, what I have is that, V minus is minus V out over A from the first expression up there, minus V out, so that's the left side, is equal to I1, so V in plus V out over AV naught divided by R1 times R2. And then I move all of the V in to one side of the equation, all of the V out to the other side of the equation. I can show that V out times 1 plus 1 over AV naught plus R2 over R1 times 1 over AV naught okay? And then if I want to write the expression for the gain, I can see that V out over V in is going to be given by this expression. So minus R2 over R1 divided by 1 plus, I'm going to factor out AV naught here, 1 plus R2 over R1. Okay? So this is my new gain expression if I have a finite open loop gain or finite AV naught. you can see that if AV0 goes to infinity, this term goes to 0, and I have the equation that I had before. Right? So I'm going to go back to minus over R2 over R1 for the gain of this circuit. Now, and then you can do the same analysis for the non-inverting configuration. I suggest you do that. And you can see that, even then for that, the gain will be reduced by the same factor that you see here. So that shows up in that equation in that, for that circuit as well. So finite AV0 will be a bit of a problem. Now, let's see how much of a problem it is. This term, let's going to assume that I'm getting some gain out of this circuit. So R2 is larger than R1 by some factor, right? But let's say significantly larger, so that this one is negligible when you compare it to R2 over R1. So this is, I can approximate it. I want to see when this is going to be a problem, right? So I'm going to approximate it with this, minus R2 over R1 divided by 1 plus R2 over R1 over AV0. Okay? So that's my answer. So as long as this ratio, as long as this fraction is negligible when I'm adding it to 1, I don't really have to worry too much about the finite gain. What does that mean? As long as R2 over R1 is significantly less than AV0, all right? I don't have to worry about the open loop gain, the finite open loop gain. So if you're getting a gain of, let's say, 100 out of your amplifier and your open loop gain is 1,000,000, well, this fraction is going to be 1 over 10,000. And it's easily negligible compared to 1, and basically you don't really have to worry about it. But if you're trying to make a circuit, let's say you're amplifying a signal whose output is, let's say coming from a thermocouple, you're talking about microvolts here, and you want to increase this by a factor of 1,000,000. Right there it tells you that it's not a good idea to use a single op-amp for that job. So if you have a gain of 1,000,000, and let's say your open loop gain is 10,000, you're going to have a problem here, right? So your fraction is not negligible compared to 1 anymore. Your gain will drop significantly. Instead of a gain of 1,000,000, maybe you're getting a gain of, let's say, 100,000. So it's a significant deviation from what you expected. And the reason is that, your op-amp cannot handle it anymore. So in a case like that, what you can do is that you can divide the task between 2 amplifier stages. So have a gain of, let's say, 1,000 for the first amplifier stage, go from a microvolt to a millivolt, and then have another stage with a gain of 1,000 and go from a millivolt to a volt if you need to. And in both cases, 1,000 is significantly less than a 1,000,000. You should be okay. And as I said, you have the same situation with the non-inverting configuration. The gain drops by the same factor, but the same argument applies. As long as you're not extracting too much gain out of that op-amp, as long as you're not pushing it to the limit, as long as, let's say, AV0 is 10 times, maybe 100 times larger than the ratio of the resistors, you should be fine. And the open loop gain, the finite open loop gain, does not affect you that significantly. So that was the first ideal, op-amp assumption that we dealt with, and we saw that, in practical cases, fortunately, it's not that much of a limitation or that much of a bad assumption after all. The second assumption, the second issue that we are going to talk about is, let me talk about offset voltages. Yeah. The op-amp offset voltage. So what this is that it says you will measure a voltage at the output of an op-amp, a DC voltage, even though there is not any input applied to it. So if you go and make a circuit like this, let's say, let's just use a non-inverting example in this case, and zero the input. This could be inverting or non-inverting actually, right? and 0 the input, you still measure a DC voltage at the output. And even if you set the gain to 1 for the non-inverting case, by opening R1 and shorting R2, you still measure some DC voltage. This DC voltage is relatively small. It's only a few millivolts in most situations or less. In a good op-amp, it's less than a millivolt. But it can be a big problem, and we'll see an example why. But if you just go to the situation where the gain is 1 and measure that output voltage, that is called the offset voltage of your op-amp. And the way that we model that is that we add it usually to the non-inverting terminal of your op-amp. So usually you just represent that voltage at the output by adding a offset voltage source here. Now here is the problem with this offset voltage source. If it was, a known voltage, let's say 3 millivolts, and we knew how much it was, we would cancel it. We would find a way to cancel it. One way is, for example, by using a adder that we learned about in the previous lecture. We would add enough negative voltage to it to cancel it out, and we would be done. The problem is that V offset is somewhat a random value. So it changes from device to device, from op-amp to op-amp. It can be positive or negative if you go from one op-amp to another. I'm talking about same part number, right? So let's say LM741 or UA741. This is a very well-known op-amp that I've been in use for about 50 years now. Two 741 op-amps will have two different offset voltages. So if you want to cancel that, you have to do a manual calibration for all of those circuits, which is expensive, time-consuming, and undesired. And there's really no way to go around it. So the only way to get better offset, there are two solutions. The first one is that some op-amps let you tune the output offset voltage by usually using a potentiometer, a variable resistor between 3 pins. 741 is one of them. What they do is that the reason that we have an offset voltage usually comes from the asymmetries that you have at the input stage of these amplifiers. And those asymmetries are, as I said, offset voltage is a DC problem. Those asymmetries come from, let's say, a tiny variation in the sizes of the transistors that you may have at the input, or a tiny variation in how they're fabricated, even though they're side by side, or a slight variation in the performance of the two branches of a differential amplifier because, let's say, you're feeding the base current into one and not into the other. It's usually a systemic problem if it is coming from biasing, but there's also some randomness to it because of the variations that I mentioned. And it's a DC problem. Once it is there, it is there. You're going to measure that DC voltage forever. The way to deal with it is, in some cases, the designers of these circuits let you play with the biasing of the circuit a little bit. So you pass a little bit of extra current in this branch or the other branch. And by doing that, you usually have access to the biasing network through 3 inputs. By playing with the biasing of the circuit, which is again a DC performance issue, you can monitor the output and make sure the output voltage drops to 0. So you manually set the offset to 0. While this is possible, it's not really doable in most cases because, well, even if you do that at some point, if the temperature in the room changes, there's a chance that the offset voltage will change, and then you get a different value at the output. So you really cannot make sure that it is gone for all voltages or all conditions, even if you do the manual calibration. The second approach to deal with the offset voltage is to just get a different op-amp and then just go and choose an op-amp. You have a ton of op-amps available to you nowadays. Each manufacturer of these integrated circuits has a library of op-amps, and especially the newer op-amps are not really that much more expensive than the old ones, but they may have a significantly smaller offset voltage. And the way that they have lower offset voltage, they can deal with it in 2 ways. In one situation, they basically get a better hang on the manufacturing techniques, so they got rid of all those randomness intolerances and all that, so they get a better offset at the output. In a second case, or another approach, is that they actually have circuitry inside the op-amp that actively monitors the offset voltage at the output and plays with the biasing as the user did in the manual case to compensate for those changes and ensure the output offset voltage is 0. So the offset voltage is there, you have to deal with it, and I think your best bet in most situations to get rid of it or reduce its effect on your circuit performance is to just choose a better op-amp. You have tons of options available to you nowadays. Now, if you have to deal with the offset voltage, this is how you model it in your circuit. You add a voltage source in series. Usually the non-inverting input is the easier one to put it. You can put it at the inverting or non-inverting input, and there's no difference in what you will have in terms of the output calculations. As a practice, maybe put it there and see if it makes any difference. But the non-inverting input, sometimes you ground it, sometimes you put it in series with the voltage source at the input, and it's just easier to have the offset in there as well. The non-inverting input, the inverting input is where you apply the feedback from the output. Usually the circuit around that input node is more complex, more complicated, and you just don't want to add complexity by adding a voltage source there. So this is how you model it, and this is really it about the offset voltage. Now what happens is that let's just go through an example and see how it can make life difficult. Let's assume that you have that situation that I mentioned, that you have a thermocouple that is producing microvolt level signals. You want to amplify this by a gain of 1,000,000 to get down up to, let's say, volt levels, right? And then because we said you may have situations, if you want a gain of 1,000,000, you really cannot take it from one op-amp, because then you're basically getting close to the open loop gain of the op-amp. You divide the gain between two op-amps, let's say 1,000 R here and R there. So this gives you a gain of 1,000, and then to get your gain of 1,000,000, you go and put another op-amp after that, and same situation, right? 1,000 R and 1 R. Or if you're using a non-inverting amplifier, so this is 999 R, right? And then because the gain is 1 plus R2 over R1. So this gives you a gain of 1,000, and this gives you a gain of 1,000. And you go from a microvolt level signal here to volt levels here. So everything looks good on paper. You go and build the circuit, and you see that the op-amp is saturated, meaning that the output of the op-amp, especially the second op-amp, most likely is either at the positive supply or very close to it, or at the negative supply or very close to it. And you wonder why. Even with a 0 voltage at the input, if you ground the input, the situation doesn't change. And the reason that happens is the offset voltage. So let's assume that, just assume that V offset, you chose a relatively good op-amp, and it has an offset of only 1 millivolt. Right? So you go and add this op-amp to your circuit, and then that should make it clear very quickly what is going on and what is causing the problem. And as I said, because the offset voltage has some randomness to it in sign and all that, the sign of the V offset doesn't really matter much. You just have, let's say, the offset voltage is plus and minus 1 volt, 1 millivolt. The sign that we put here on the symbol here is so that we take care of our currents and voltages as they propagate through the system. So with an offset voltage of 1 millivolt, even if your source is not producing anything, you get a DC voltage of so even without a signal, you have somewhere on the order of 1 volt. A signal as much as 1 volt, a DC voltage as much as 1 volt at the output of the first stage. Well, that's bad news for the second stage, because this guy also has a gain of 1,000. So it is faithful, it looks at the signal, it is a 1 volt signal. To the second op-amp, it's a signal, right? It doesn't know that it's a offset voltage and it should be discarded. Goes and tries to make 1,000 volts at the output of the second op-amp. Well, obviously you don't have that much headroom. let's say plus or minus 5 volts or plus or minus 3 volts, and it wants to go all the way to 1000, you stop it at 5 volts, well, that's saturation. Your op-amp saturates. You have seen that for transistor circuits, right? You cannot really go above the power supply. So the output saturates, and then you are stuck. You're basically, the second op-amp is not in its linear range anymore. It doesn't respond to the changes at the input. So even if your input starts to change, you won't see it. Now the bad news here is that, when I say it is 1 millivolt, it means it is some number between plus and minus 1 millivolt. It could be half a millivolt, it could be 0.25 millivolt, it could be 1, it could be minus 0.75, or it could be 0 if you're lucky, right? But it could be anything. So this voltage here is not really 1 volt. If I knew it was 1 volt, I would cancel it at the input of the second op-amp. I don't know what it is. And then the second op-amp actually has its own offset that is added to it, so it's going to be plus or minus 1, maybe plus or minus 1000 from the first stage, plus and minus 1 from the second stage, but that one really doesn't matter. All the problems started from the first stage anyway. And your only solution in this case is, if you're interested in some low frequency signal like the thermocouple that I mentioned, your only solution is to change your op-amp. There's really, other than manual calibration, which we saw is not a good idea, your only solution is to change your op-amp. Another thing that may help you if your signal is AC, so let's say instead of a thermocouple, the signal is actually coming from an antenna, and you have an op-amp that is fast enough that it can apply that RF signal, amplify that RF signal. In that case, life is easier. What you can do is, in between these two op-amps, you can have a coupling capacitor that you have seen before. A coupling capacitor separates the DC from the two stages, right? So the two stages are not affected by the DC signal from one side to the other. So even if you have a DC voltage produced at the output of the first op-amp, it doesn't affect the second op-amp. The second op-amp doesn't see it. The AC signal that is produced here goes through this capacitor and reaches the second op-amp. Now there is still a problem with this circuit. If you look at the non-inverting input of the second op-amp, this circuit here, it's left open because a capacitor is open circuit at DC. You have a floating node. It's called the floating node. The voltage at that node is not determined, right? Because the input resistance of the op-amp is infinite. It doesn't draw any current. The voltage source over there is floating. The voltage is undefined. So to avoid that kind of a problem, usually you put a pull-down resistor here. Usually you choose this value to be large. So let's just call it the R pull-down. And you set the voltage to 0 volts to avoid any kind of a random voltage on that node that can mess up your circuit. Okay. So that's the issue of input offset voltage. The other problem that we have, or the other assumption that we had, was that the input resistance of an op-amp is infinite. Now, from the small signal point of view, that actually is usually a good assumption. As it turns out, when you use feedback around the op-amp, what you do is that you go and trade that really, really large input open loop gain of the op-amp with stability. So you go and use feedback to trade off the gain for stability. You get a gain that only depends on the ratio of R2 and R1. And hopefully in more advanced courses on circuit analysis, you'll learn how to deal with feedback in a more formal way. But that's actually what is happening. The feedback loop that you created here reduces the gain, the overall gain of the circuit, by sacrificing or by utilizing some of the gain that you had inherently without feedback. Another thing that it does in a circuit like this, especially like non-inverting configuration, is that it increases your input resistance by the same factor. So let's say if your gain goes from 1,000,000 to 100 in your circuit, your input resistance, if it was, let's say, 100 megohms at the beginning, now it goes up by a factor of 10 to the 4. So a million to 100 is 10 to the 4. You reduce the gain that much. Your input resistance actually goes up by the same factor. So you go from 100 megohm to maybe 1,000 gigohms. Basically infinite, right? Basically open circuit for the small signal. And then actually the good news is that your output resistance also goes down by the same factor as determined by your feedback network. However, for DC point of view, from the DC perspective, just using this circuit under normal DC conditions, the input resistance, we don't talk about it, we talk about the current. The input current is not really zero. And we call that input bias current. Why? It's a bias problem, it's a DC problem. Where does it come from? Well, you're using a voltage amplifier here. We saw from the transistor amplifier discussion that you have two choices. If you have a voltage amplifier and you want to have a very large input resistance, which we want for an op-amp, you either have to use a common emitter stage or a common collector stage. We normally use a common emitter stage because I want to get some gain, some voltage gain, while everything else is happening. So I will use a common emitter stage at the input of my amplifier to get a high input resistance and high voltage gain. I deal with the high output resistance of the common emitter stage later on. But a common emitter stage, well, the signal goes into the base. And the base, you need to bias the transistor. So whatever IC that you establish, the current that goes into the base is going to be there. So this is more of a problem for the old op-amps that used BJT technology. The new op-amps actually, we know, that are using MOSFETs. And for a MOSFET circuit, you know, if you want to make the same configuration using a MOSFET, you probably use a common gate or a common drain stage, but common source or common drain stage, but for the same reason that we talked about, you probably use a common source stage. You want to get some gain as well as high input resistance. And the gate of a MOSFET draws no current. So the input bias current for a MOSFET is going to be zero. For the older op-amps or some of the special high-speed op-amps that you make with BJTs, you get some current that goes into the base, to the terminals of these devices. I just want to be consistent, so it's called IB1 here and IB2 here. So the way we model these is as two independent current sources that are put in parallel with the inputs, right? And then V out, amplifies the difference. But I have two IB1 and IB2s that are going into the inputs of this transistor, this op-amp, and I modeled them using two current sources. I know these are the base currents, so it's, a current source is not really a good model, maybe not. But if you go and look at these op-amps closely, IC is usually generated using a current source that's a fixed current. If your beta is fixed, your IB is going to be fixed. And therefore, a current source model for the input bias current is probably a good assumption. Now, what happens with the input bias current is that we have two different ones, one for each input. In most cases, you can assume they have relatively similar values. The direction of the current is not random. It depends on the input stage that you choose. So for example, if you have NPN transistors at the input, IB goes in. If you have PNP transistors, IB comes out. So the direction is not random. The values are very close, but there could be a little bit of difference between them. So you have two issues. You have an issue of input bias current, and then there is an issue of input bias current offset. There is a difference between the two. We're not going to talk about that. We just want to deal with input bias current. Now, as you go and make a circuit using this then you can see that this is going to give you a little bit of a headache. So let's say if you go and make a non-inverting amplifier using this OpAmp, I'm going to add the input bias current sources inside the OpAmp. You can put them outside as long as you know this is something that is happening inside. You know, keep that one in mind, that this is something happening inside the amplifier. It's not external to it. So assuming that IB1 is equal to IB2, right? So I'm going to ignore the possible difference that I may have between the two of them. Then what you can see is that even when the input is grounded, even when the input is 0, what is going to happen is that, well, assuming that your assumption of the infinite input voltage gain is there, the virtual short between the two inputs means that here you have a virtual ground, but IB1 in this case is going in. So you have a current IB1 that is going in. This current IB1, well, for this resistor R1, you have 0 volt at the right end, 0 volt at the left end, so there is no current going through R1. All of IB1 goes through R2. You can see that V out is going to be equal to, IB1 R2. Okay, so you get a voltage at the output, and this is a DC voltage again, produced by the bias current that you have at the input. The values for typical op-amps, even the old op-amps, are on the order of nanoamps, maybe in the worst case microamps. So as long as you are not using large resistors, this is probably negligible. But let's say if you're using a 1 mega ohm resistor for your R2 and the IB1 is, let's say, 100 nanoamps, you're going to have a 0.1 volt voltage at the output of your op-amp without any signal applied to it. And to make the matters worse, you will have the effect of offset voltage on top of that, and they're usually indistinguishable. So people try to come up with ways to cancel that. What you can do here is, for example, the first thing you can do is you can go and say, well, let me do this. I'm going to add a voltage source here to my non-inverting input. I'm using one example. I'm going to show you one example so that you get the idea for this approach. Let's say I'm going to use a voltage source here. Let's just call it V correction. That is going to be large enough for the same value that is needed to make the output 0 under these operating conditions. So how much this V correction should be? Well, where does that voltage at the output come from? IB1 flew through R2. That's the reason I have a voltage at the output. If I make all of IB1 go through R1, I will not have that problem, right? If I make so let me use superposition here and see what should be the right value for V correction to make V out 0. So V out in this case, from the expression in the above, I have IB1 R2. And notice IB2 doesn't matter in this case because it's input in, basically it's either grounded or put in parallel with the voltage source. So IB2 doesn't play a role. But if I apply superposition and apply IB1 first and then V correction second, with V correction applied like this, I will have that much gain for it, right? My goal is to set V out to 0. So I want V out to be 0 when I have not applied any signal to it. So V correction is a signal or voltage source that I want to produce in order to get that output to 0 before the signal comes in. So I can see that V correction should be IB1 R2 divided by 1 plus R2 over R1. Okay? Divide everything by R2, so it's going to be IB1 divided by 1 over R1 plus 1 over R2. And this should ring a bell. It's as if I have a combination of two parallel resistors. So the value of V correction should be this much. Okay? So this is how much voltage I should apply there to produce that correction voltage that I need in order to make the output zero for that came from the input bias current. Now the problem here is that, knowing that IB1 is small, with R1 and R2 values, let's say in the kilo ohm ranges, and IB1 in the nanoamp ranges, you're talking about microvolt type of a correction voltage, which is really inconvenient to produce. But looking at this and knowing what we know from the above should give you an idea of how I can actually create that voltage with some components. So I'll give you a second to think about it, and then I'll give you the answer or one solution to producing the proper V correction to cancel the effect of I bias. So what we can do is that note that IB1 and IB2 are almost equal, right? So this is the input bias current to two inputs. The transistors are usually biased similarly, so they're about the same value. And if they're about the same value and I want to produce this correction voltage that is this much, what I can do is go and take I make my circuit as before. And to produce that correction voltage, I use a resistor value that is equal to R1 over R2. Right? Now, if you notice, I will automatically produce the right amount of the correction voltage at that second input, as long as IB1 and IB2 are more or less the same, which is a good assumption. So I had a systemic problem, and because I knew this was not like the offset voltage issue. The offset voltage, it's random sign, random value all the time and all those things. But in here, I have a systemic problem. I have an IB1 that goes into the op-amp. I can measure that IB1. I know IB2 is almost equal to IB1. Because I know these things about it, I can come up with this solution. And therefore, by putting a value, a resistor here, an extra resistor in series with the second input, I can produce that V correction automatically and take care of the effect of IB1 on the output. If you look at your book, there are other examples of how they canceled or compensated for the effect of IB1 in other circuits and other topologies, but this is the approach. So you look at the output voltage from the op-amp, you decide to correct it somewhere in your circuit by usually maybe adding a voltage source, and then you go and figure out how much resistance you need in order to basically compensate for the effect of I bias in one input using I bias in the second input. Now, all that said, if I bias is a consideration, if I bias is annoying you for whatever reason, my best solution to you, my first suggestion to you is to use a different op-amp. So you can get op-amps nowadays. If it is a CMOS op-amp, the input bias current is on the order of sub-nanoamp. Picoamps is typical. And if you really, really are interested, you can find op-amps that have femtoamps of input bias current, which in most cases is really zero. It's not going to affect most circuits. So even if you have a 1 gigohm feedback resistor, a 1 femtoamp current gives you 1 microvolt of voltage drop across it. The noise from that resistor is larger than that. So if you're really put in a corner, go and choose a different op-amp. And if that's not possible, if you're doing something at home, doing something hobby, and you don't want to wait for the component to arrive, here is a solution that you can use to compensate for IB issues. V offset, unfortunately, there's really no problem, no solution to it that you can apply, in all cases. It's not a systemic problem, it's a random problem. And your only choice really is to choose a better op-amp. Okay. Now, we talked about the saturation of the voltage at the output, so this is another non-ideality. An ideal op-amp should be able to give you any voltage at its output. A real op-amp is limited to the power supplies that you have, right? So if it is a dual supply op-amp plus and minus 5 volt, your output voltage cannot go above plus and minus 5. So from things that you learned in transistor sections, you know that if you use a transistor, a BJT at the output stage, the minimum voltage you can have is one saturation voltage for that transistor above the power supply. If you have an emitter resistor, that's actually even worse. So you really can't even get to the power supply voltages, right? So if you have plus and minus 5, maybe the output voltage is limited to plus or minus 4.5 or something like that. And that's a limitation that you have to keep in mind, that, you know, what is the dynamic range at the output? What are the requirements? You know, can I get that with the op-amp that I have? Do I need an extra, let's say, half a volt or so? And then if it is a limitation, again, there are op-amps out there that are, their outputs are called rail to rail. They go from the positive to the negative supply all the way to that, in that range. And you can choose one of those op-amps. And as always, there's always give and take, right? So you get one property, you may lose something else. But there are op-amps in these situations that you can go and pick. Typically, the output of these op-amps is can be assumed to be the output of an ideal voltage source. So usually they have a few ohms of output resistance, but as I said, it is divided by the feedback factor. So let's say if you have an open loop gain of a million and a closed loop gain of 100, the feedback factor ratio is about 10,000. So the 5 ohm output resistance that you have is divided by that. It's 5 milliohm. It's negligible in most cases and can be assumed to be 0. So the output, on the output side, the op-amps are really, really close to an ideal op-amp. However, that doesn't mean that they can give you any current that you want. It's not an ideal voltage source anymore, right? It's not really an ideal voltage source. It is still the, you know, by this point, an op-amp, you know, a transistor. So there is a limit on how much current it can provide to you. Early days, op-amps didn't have this current protection, right? So you could basically draw a lot of current from that op-amp and basically kill it, right? It would overheat and the output stage would fail permanently. But most of the modern op-amps, I would say almost all of them nowadays, almost anything that you buy off the shelf has a current limit. So this is another parameter that you should look up on the spec sheet. That what is, you know, if you want to drive a load that needs 100 milliamp of current, well, can your op-amp provide that much current? Because they have current limits for their protection. And that is it for the DC imperfections of op-amps. There are two other non-ideal factors that limit the speed of an op-amp and how we can use them in AC applications. And that will be the subject for the next lecture video.